Okay, this is going to be going over VSEPR activities notes. Some of these notes are incomplete, but I'm going to go ahead and record and share this with you. So this is just set up to show you some of the different VSEPR models that there are, and we could get into the number of sigma bonds, lone pairs, and so forth. We talked about this already. These are your lone pair electrons. They're not bonded to anything, and they are noteworthy because they determine the overall shape. Okay. And that overall shape determines the bond angle, and the bond angle determines the properties that you're working with. And again, this is just more of the same. Here are some more shapes. I just filled on this one the sigma and the lone pairs and the bond angles just so you can see. If you want to, you can go to the PhET molecular shapes and click on that and play with this at your leisure to see, or I may assign it as something for you to complete. But this is an option. And this would be some of the stuff that goes with it to make sure that we're understand what's going on. So with that, I generally try to get y'all started with the VSEPR modeling, and we go through it and step through it together. And this is what our worksheet looks like. And some of these I've purposely left blank, and some of these I have filled in for you. We talked about, writing down the formula. We talked about determining the total valence electrons, the Lewis dot versus the actual structure, and how lone pair electrons affect that structure, and then the name. We also talked about how finally we're actually able to understand these polyatomics when they have these charges, how that's going to change that shape overall. And sometimes on those shapes, we get what we call a resonance structure. Okay? So, again, I left some of these blank, and I've also tried to include your resonance structures as well. So you're welcome to look through here. And then I added to this on the end with some compounds just to give you a piece of what it looks like. Okay? So, for example, here I have acetic acid, and then I give you methane. Methane is easy to tell what shape it is because you only have one center atom, whereas acetic acid, there's multiple around that. And then I have ethanol, and since ethanol has two carbons involved, two center atoms, then we have to determine on each center atom what shape we have. And so on that one, I just say, don't worry about it. And then I also threw in a benzene because a benzene ring is one that we should recognize. Benzene rings are unique, and they are 6 carbons chained together with double bonds throughout. So sometimes for the resonance structure, we'll just simply draw that with a circle on the inside to represent the double bonds are at different places. Okay. And then I also went back over the VSEPR activity, the analysis of that, where you're drawing some more of those and labeling what they are. Some of those do have resonance structures. And then you have a conclusion where I'm not going to give you the answer because I think you already know what type of bonds these are. This goes back to the fall where we talked about ionic and covalent, and we also mentioned briefly metallic. So what kind of bonds are these? How do you know that? And why is that important? Think about the properties of that. So then I also gave you another worksheet, more modeling going on. The ones that are starred, I didn't fill them all the way in because I feel like you should be able to draw those because we've already done those before. Now, this added the polar, nonpolar. The distinguishing factor on polar versus nonpolar is if I'm symmetrical. So here, it's pretty obvious that that's symmetrical because it's linear. So if I put a mirror right here, my left side looks like my right side. Sometimes when we draw the Lewis dot structure of the BF3, we can't tell automatically that it is nonpolar, but if you recall right, it's trigonal planar. And so I look at that, if I draw a line down there, I have a mirror of that image on left and right. So that's the distinguishing factor on it, is it to determine if it's polar or nonpolar. If I am symmetrical with the shape, I'm nonpolar. So I'll pick on trigonal pyramidal. Things that are trigonal pyramidal are generally going to be polar because those lone pairs make it no longer symmetrical. Okay. So, and then down at the bottom we get into the more complex ones, the ones that are to the right of our stuff on the wall up there on the ceiling. These are the more harder ones, more challenging ones. So I do put those out there and let you work with that. And that is the last part for this vestibular model.